force and a negative coefficient, or negative kinetic frictional force. And that has to equal the mass, which I know is 300 kilograms, times the x acceleration, which is 0. Because it's moving at constant speed. So lo and behold, I can find the kinetic frictional force, which is not what they asked for. They asked for the kinetic friction coefficient. So I'm going to leave this here and I'm going to do my y equation. I look at my picture. I've got a positive normal force minus gravity equal to MAY. And FG has a special equation you guys have already learned, right? The gravitational force can be written as mg. So I plug that in. What's my y acceleration? Book didn't talk about it. Is it moving this way?
Oh, no, it's 0.
No. So it's not moving up or down at all. So this is 0. Almost every problem we do, the y acceleration is 0. But I put this thing in an elevator and it's not true anymore. So don't just always make the y acceleration 0. But if the thing is moving horizontally, the y acceleration is 0. So I can write for this equation, so I've got two different equations. I've got my x equation and my y equation. And for my first equation, let's look at it first, now that I've got it written up there. I've got 385 plus 350, which is 735, minus Fk equals 0. So the frictional force has to be 735, according to equation 1. I haven't answered the question yet, but I found information. According to equation 2, the normal force times 300 kilograms times 9.8 meters per second squared has to equal 0. So I rearrange this, and I find that the normal force is 2940 newtons. So I found this from one equation, I found this from the other equation. Neither one of those is the answer to the problem, but the answer to the problem is based on those two. So I have to recognize and remember that this is also true. So I've got two of these, right? We just found that and that, so I can solve for that, which is what the book is asking for. So I've got 735 equals mu k times 2940, and I get mu k equal to 0.25. It's unitless, right? Because the Newton cancels the Newton, so I know I didn't make a mistake there. And it's less than 1, so at least I got that. I don't really know whether 0.25 is right or not, because I don't really have a good feel for static coefficient or frictional coefficients, but I know it has to be less than 1. Okay, does this make sense? So you guys have done a lot of these force problems already, haven't you? Have you done them for homework and stuff? So there's no difference. The way we're solving these problems is the same process. We just have this new force now that we're dealing with, this new frictional force. Okay. Okay, let's look at E19. So E19 is a lot harder to draw the picture for, but once you get the picture drawn, it's a lot easier problem. This is what it says. It says a 10-kilogram crate is placed on a horizontal conveyor belt. The materials are such that the static coefficient of friction is 0.5 and the kinetic coefficient of friction is 0.3. And it says draw a free body diagram showing all the forces on the crate, all the forces on the crate if the belt runs at a constant speed, if the belt is speeding up. And then it says what is the maximum acceleration the belt can have without the crate slipping. So they give us a bunch of different information. They tell us that the mass is 10 kilograms, that the static coefficient of friction is 0.5, that the kinetic coefficient of friction is 0.3. And there's this box on a conveyor belt. And the belt, the whole system is moving this way. Because the belt is moving. But this is this example of, is it static friction or coefficient or kinetic friction? Because the belt is moving, the box is moving, but they're not moving relative to one another. So there's actually a static frictional force that exists between the two of these. And the question is in what direction? This is not easy. Maybe left or right. You know that. So we know there's a normal force. We know there's a gravitational force. What's making the box move? The belt. So there's some force associated with the belt. Is that, do we consider that a pushing force? Why is there force? If the belt were made of ice, would the box move along with the belt? The belt would just slip out right from underneath it. So the thing that's making the box move in this case is actually the static coefficient force. This is one of these conceptually really difficult problems to get. Because there's friction between the box and the belt, there has to be a frictional force. That frictional force in this case is static because the two are not moving with respect to each other. Okay? But that is the force that's causing the box to move. This is the hardest, one of the hardest diagrams to draw. I'll give this on a test every once in a while, even after I've given it on homework, even after I've talked about it in class, and people have a hard time with it. Because it's really conceptually difficult to understand why it's this static frictional force that's moving it. The way I think about it is that it's that whole idea that bonding that's happening, is that this thing is sitting on the belt. It's this idea, it's the same as the book on the desk, right? Here's the book on the desk. I move the table, but the book doesn't move. Could I push this table hard enough that I could get the book to move? Oh, maybe not, but I can't. I'm too weak, but I can do it twice. I'm not too weak with the box. So here it is, I'm pushing the box with the calculator. Watch this. Right? Calculator slipped on the box in that process because I pushed so hard. So I push slow, calculator doesn't slip. I push fast, the calculator slips. That process is because of this idea of the static frictional force. If, as I move this, there's a static frictional force pushing the calculator this way, okay? Just like the box on a conveyor belt. If I push this hard enough, I can get it still moves a little bit, but not very much. And I'm getting a kinetic frictional force, right? As I get this to move, there's a kinetic frictional force there. So this is a very strange phenomenon that right now static friction pushes the calculator that way. Now, right, as it slides out from underneath it, kinetic friction pushes it that way until it falls into the box. So if I want to keep them together, I have to push at some force. If I push bigger than that force, they won't stay together anymore. If I ran my conveyor belt too fast, none of the boxes would stay on the conveyor belt. They'd all just be like slipping off of it and going crazy. So it's a slipping effect. When I push hard on this thing is slipping along this, right? It's not slipping if I push small enough. And because it's not slipping, it's a static frictional force. And there's no other force. It's not like there's some other force. There's not a person with a rope. There's nothing else pulling this thing. It's the friction of the conveyor belt that is pushing the box. So once you can get this picture, the problem is incredibly easy. But it's a really hard problem until you can get this picture drawn. So this is where it says, draw the picture if the conveyor belt runs at constant speed. And then it says, draw the picture if the conveyor belt is speeding up. Well, as long as the box is not slipping on the conveyor belt, then the speeds are the same. Or the pictures are the same. So this is the same for speeding constant or speeding up, as long as box is not slipping. At some point, the conveyor belt could move fast enough that it starts to slip, and then it's a different picture. then there's a kinetic frictional force on it. Questions about this? This is one of these things I always tell my students, go try to explain this to somebody else. If you have somebody that you study with in this class, like try to explain it to each other. And if you can, you're good. If you can't, think about it some more. And it seems kind of weird. That's a weird process to sit there and go, I'm going to explain this conveyor belt problem to you now. But like, it's one of those things that if you can't verbalize it to teach it to someone, you do not know it. A lot of times you think you know it in your head, and then you get to the test and you get the question wrong because you don't really know it. If you can speak it out loud, you know it. Okay? Okay, so let's do the problem. Or do we have to do the problem? It says, what is the maximum acceleration the boat can have without the crate slipping? Okay. So max acceleration without crate slipping. And the reason they talk about it this way is because this is the maximum static frictional force. The instant it starts to slip, it's kinetic friction. So we're pushing it, the conveyor belt is pushing along and accelerating along to some maximum value at the instant before it starts to slip. So that means that we can think about the maximum static frictional force, which is easier mathematically because we know that that's equal to mu s Fn. Okay, so I'm going to do my little same procedure as before. So once I have the picture, the process is the same. If you can get the picture, the problem-solving process is the same for every problem in the universe. The pictures are part of my picture. So I'm going to do my x direction and my y direction, and I'm thinking about the second one. So in the x direction, the only force I have is the static frictional force, and it has to equal max. In the y direction, I've got a normal force up, a gravitational force down, and that has to equal may. And my y acceleration is 0 for the same reason it was in the other problem, that the box is not moving up or down. So this one is 0. So I have two equations to think about. So equation 1, I can plug in my special equation for the static frictional force. I know I'm dealing with the max, so I can write it as mu s Fn equals max. And I have a special equation for gravity too, which I can plug in to equation 2. And these are linked through the normal force. The x and y direction are linked through the normal force, which is really common in the problems that you guys do. So equation 2 tells me that the normal force is just mg for this particular problem. Not always true, but for this particular problem. So I can write equation 1 out as mu s mg equals max. I'm purposely doing it with algebra instead of numbers, because I want you to see that the masses cancel. They told us the mass of the box, but the masses actually cancel. And the reason that this is important is because if you're UPS and you have conveyor belts running all over an airport to move boxes to different places, you don't want to have to know how much the box weighs and what the mass of the box is in order to determine how fast your conveyor belt can move, right? So the speed that the conveyor belt can move without any of the boxes slipping off is the same. It doesn't matter what the box's mass is. And so you can see that only if you solve this problem with algebra. If you started plugging numbers in early, you wouldn't notice that. So I end up with the acceleration equal to mu s times g. And mu s was given in the problem, and g I know, so I can find this value for this ax. I get AX equal to 0.5 times 9.8 meters per second squared. So I get 4 point, it's 9.8 divided by 2. Good God, I cannot do basic math anymore. This is what happens when you get old. What's up? I used to be really good at like basic math. I can't do it. It's embarrassing. Okay, so this is the maximum acceleration that you can accelerate your conveyor belt at without the boxes starting to slip. You can obviously do it at less than this, but this is the maximum. So again, I think, at least the hard part of the problem is the picture. Once you get the picture, it's the same process over and over and everything. Okay? So let's go. This is a good one. Let's look at 45. This is a tough one. 45 is with an incline plane. You guys have done incline plane force problems already? No? Yeah? Okay. 45 says it's moving day, and you need to push a 100-kilogram box up the 20-degree ramp into the truck. The coefficient of friction for your box on the ramp is 0.9 static and 0.6 kinetic. Your largest pushing force is 1,000 newtons. Can you get the box into the truck without assistance if you get a running start at the ramp? And can you get the box into up the ramp without the moving start? If you stop on the ramp, will you be able to keep it going? Will you be able to start again? So you can imagine here I've got this heavy thing, I'm trying to push up this ramp in the moving truck. I'm going to get a running start, so I'm going to start moving it on the surface, right? And then head up the ramp. And I'm going to push it, it's going to go slower and slower, right, as I push this thing up the ramp, because I'm pushing as hard as I can. And then if it stops, am I screwed? Like if it stops, am I going to have to come back down the ramp with it because I can't get it started again, because we know it's harder to get something started than it is to keep it going. So that's what they want to know. Okay, so I've got a ramp. They tell us it's a 20-degree angle. We've got an object on the ramp. Presumably I've got it on the ramp already. And I am pushing it. In addition, there's gravity. Gravity points straight down. There is a surface contact. And previously, when we thought of surface contact, we only thought normal force. But now, if there's a surface contact, you should think normal force and friction, because both of those things are due to surface contact. So the normal force points perpendicular to the surface, so off at this weird angle. And then there's some frictional force, and I'm just going to call it F for now. I'm not going to designate whether it's static or kinetic, because they asked me two different questions. They said, as it's moving up the ramp, right? And then they said, what if it stops? So I'm just going to think about this. There's some frictional force. It depends on whether it's moving or not, with whether that's static or connected. So I'm just going to keep it as F. And with inclined plane problems, you guys have learned that the easy way to do it is to rotate your axes like this. You don't have to, but the problem is a lot harder if you don't do this. This just makes the math easier. So because I've rotated my axes like this, my gravitational force is in a weird direction. These two are along the x and negative x. This is along the positive y, but this one is weird. So this is the one I've got to split up into components. And this, so my students mess this up in two different ways. My students draw the wrong triangle. I'll have students a lot of times draw a triangle that looks like this. That is not the right triangle. So how do I know that that is not the right triangle? Like, how do I know how to draw my triangle? You guys know? Because you've memorized it? No, it's not good. Because I'm trying to figure out the x and y component. So I want the sides of my triangle to be along the x and along the y. Because that's the purpose of the triangle, is to figure out the x and the y part. So if I'm going to draw the triangle so that their sides are along the x and the y, I only have one choice with how to draw the triangle. This side is along the y, and to get along the x, I've got to go like this. That's why the triangle has the shape that it does. It's because you're trying to get this x side and this y side. So this is my right angle, right there. Or you can memorize it, which you should know, especially if you're a physics major. So this angle right here is the same as the incline, and that is a really easy proof to do. I make my students do that proof with Google geometry. You just draw a bunch of triangles and you can show that that's the case. Or you can memorize it. So this side here is opposite the 20 degrees, so it's the sine side. So I write this as FG sine theta, or sine 20 in this case. And this side is the cosine side, so it's, let me keep this theta. So it's FG cosine theta. Okay, so I've drawn the picture, I've drawn my axis the way I want it to be. I've split up the one force that wasn't in the x or y, I've split it up into x and y. And now I can go through this same process of doing my x direction and my y direction. So just like all these other problems we've been doing, I'm thinking the second law. And I'm thinking it in both the x and y direction. So I look at the x direction and I've got a pushing force that's positive, a frictional force that's negative, and part of gravity. And is gravity that Fg sine theta? Is it acting to pull the box down the ramp or up the ramp? Down. Down, so it's got to be a negative. Those are the only three things in my x direction. So that's my net force, and it has to equal max. Then I look at my y direction. I've got the normal force. It's pointing in the y direction. And I've got the cosine component of the gravitational force that's pointing in the negative. Right? It's pushing, the gravity pushes the box down into the incline, not up, out of the incline. This is an example where the normal force does not equal the gravitational force. And I have students, my students so often will not write this equation out, and then they just tell me that the normal force is the gravitational force, because they're so used to seeing it, but not in this case, it's not true. Okay, so what we know for sure is that this thing is not, it's moving in this direction, which is the x direction. It's not moving in this direction at all. And so I can say that this acceleration is 0. It is moving up, but up is no longer the y direction. Okay, the only other thing I can really do at this point without getting more specific is I can plug in my special equation for gravity. I know Fg is mg. So I'm going to call these 1 and 2. So my first equation I can write F push minus friction minus mg sine equals max. And for my second one, I can write normal minus mg cosine equals 0. And it's at this point that I have to know, is it static or kinetic friction? Because that changes things. And I have to know, is it accelerating or not accelerating at the ramp? Right, I got to know both of those things. So I go back to the problem, and it says, can you get the box into the truck without assistance if you get a running start up the ramp? So let's talk about the running start idea. So if we get a running start, that implies that the box is in motion, right? I'm not at rest on the incline, the box is in motion. So this tells me that friction is kinetic, and I can write it as mu kFn. solve this problem. The first is, what is the acceleration if I push with my maximum push force of 1,000 newtons, as given in the problem? So it says, can you get it up the ramp, basically? So I'm pushing with my maximum force, my maximum push force. If the acceleration is 0, I'm probably okay because I'm moving at constant speed. If the acceleration is positive, it means I'm accelerating it up the ramp, so I'm good to go. But if the acceleration is negative, it implies that it's actually coming back down the ramp, right? Or it's slowing down and will eventually come back down the ramp. So that's one way to think about this problem. The second way to think about it is, what push force is required to move it at constant speed up the ramp, which is the easiest, right? That's the easiest thing to do, is to move it at constant speed. So what push force is required to move it at constant speed up the ramp? And if that push force is 2,000, and I can only push it 1,000, then I'm not going to get it up. If the push force is 800 and I can push it 1,000, I'm good to go. So you can do it either way. This is not necessarily, this is one of these problems where the picture is maybe easier than solving the problem. Because coming up with how am I supposed to answer this is kind of tough. I think the second way is easier, so let's look at that. So I go back to my equations. I've got F push. So this is for the second method. I've got F push minus UKFN. I know it's kinetic friction now. Minus mg sine theta equals 0, because I'm choosing to think about it at constant speed. So the acceleration is 0. Now, what do I know? If I look back at the problem, they give me the mass. They give me, well, we know g. They give me the angle. They give me the mu. So I'm actually missing both of these things, and this is the goal. The goal is the push force. So I've got to somehow figure out the normal force. Thankfully, I have a second equation. So the second equation tells me that the normal force is mg cosine theta. Again, I've got the mass. I know g. I know my theta. So because you guys should be thinking algebraically, as it makes life a little bit easier, you can do it. I can write out that my push force minus mu k mg cosine theta minus mg sine theta equals 0. So I just plugged my normal force into that first equation. And I've got all these values. I have theta, g, m, theta, g, m, mu, and I can find the answer. And if I go through and do that, which you guys can do, I get a push force of 887.7 newtons, which is less than this person can push. This person can push at 1,000.
If you have a running start, can you solve the negative acceleration and technically make it up the ramp?
That's a good question. It depends on the length of the ramp, right? So he's right. If I have a running start, it completely depends on the velocity that I get at the bottom, right? With whether or not I can get it into the thing. This is why I hate textbooks sometimes, because they didn't mention any of that.
Yeah.
And so in my brain, I'm like, okay, screw it, we're not going to think about the length of the ramp. Let's just assume the ramp is t, right? So that, or really long, I guess. Let's assume the ramp is really long. But that's not an obvious thing when you haven't been teaching physics for 20 years. So all I can say to you guys is, if you have a question like that, I always tell my students to email me. Like if you start thinking like that and you're trying to figure out, doesn't it depend on the length of the ramp? Like I say, shoot me an email and ask me that. And I'm sure Dr. Houston would be happy to talk to you about that. But he's right. You could technically have it slowing down, and if the ramp is short enough, right, you could still make it to the top. So. Okay, so the rest of the problem asks about it being at rest on the incline. It says, if you stop on the ramp, I don't know why you would, because you're perfectly capable. Let's say you're starting to get tired, right? If you stop on the ramp, will you be able to get the box moving again? So we're gonna, these equations are still valid, right? Because I haven't, this was my general equations. I haven't plugged in my frictional force yet, so I can still use these equations. So I'm gonna start here for the at rest on the incline part. And really, I guess it's these two, right? Because I've already plugged in my gravity. So let's start here. So the difference between those and those is I just plugged in Fg equals mg into there. So I got these equations to start from. This is where we started thinking about it as moving up the incline. And now we have stopped on the incline. Because we've stopped on the incline, the frictional force, which I just have F, which we used kinetic friction for the last bit, now we're using static friction. So F is F static. And we're going to assume the maximum static friction because we're trying to get it to move. So we got to figure out, can we push hard enough to overcome friction? So we're going to use Fs max, which is mu s F. Now, the other nice thing when it's at rest is that the x acceleration is 0. Right? We're at rest, so we know ax is 0 as well. So I'm going to go through the same process. Like, what pushing force do I need in order to overcome the maximum static friction? So that's what we're going to think about. What F push is required to overcome the Fs max, which is the whole reason I'm putting the Fs max into the problem. Okay, so I'm looking at my equations. I've got F push minus mu s Fn minus mg sine theta equals 0. And for 2, I get normal force is mg cosine theta. And I'm linked through my normal force, so I plug it in. This is the exact same equation we had before. The only difference is that it's the static coefficient of friction instead of the kinetic. So the answer is not the same, because it's mu s instead of mu k. But we've got all those values. I know theta, I know m, I know g, I know my mu s. So I end up with so I better not stop. So if I stopped, if I'm this person, if I stopped on a ramp, I actually couldn't get it going again. I would have to bring it back down the ramp, get my running start, and go again. And then I could get it in. This is one of the harder frictional problems, right? I mean, this is, the pictures are tough on this one. What's tough on this one is kind of deciding what the words mean. It's the word problem again, right? What do the words mean? What are they asking? And how can I figure it out? Questions?